So, welcome to session number 4 of module 5, in which we are discussing design of power screws. So, in the previous sessions, we have seen the different concepts or different introduction to power screws, types of power screws, what are their functions, and also we have seen the stresses developed in the power screws. And now we will apply those equations or analysis to solve some particular applications or to design particular devices using the power screws. So we have one example here, a solved example where this is a screw jack, the upper part of the screw jack. So we have in the screw jack we have this cup, and this is a bearing surface. On this the load has to be carried by the screw rod or the power screw. And in the machine drawing we might have done all the drawing of these components, and we have the collar here, and we have the handle or the lever to apply the torque on this screw rod here. So this is a screw rod, and it's having a threads, and this is a collar, and this is a load it has to carry. So here we have the device, and it is telling that this is a square thread. So power screw is having a square thread, and it is double start square thread, and the diameter is given 24 mm outer diameter, and pitch is given as 5 millimeter. So these are the parameters or dimensions of the square thread screw, and it is operated by lever. So we have this handlebar or lever of 200 mm length, and the maximum effort that can be applied at the end of the lever is 250 Newton. So here, using this lever or the handlebar, we are applying around 250 Newton, or we are trying to rotate this screw by applying a force of 250 Newton here. And coefficient of friction at the screw thread is given here. So the coefficient of friction is given at the threads here, and it is 0.12. So what we have to find out is we have to determine how much load we can lift while rotating this power screw, and he is telling us to that collar friction has to be neglected, and we have to check whether the device is self-locked or not. So we have to check for self-locking or overhauling of the power screw while it is operating to hold this load W. So how much load it can hold, that we have to find out here. So here to begin with, let us take the given data to let us study or let us understand what is the given data here. So the diameter D is given 24 mm. So this is the outer diameter of the screw thread, and D1 is the inner diameter of the screw thread, and D is the mean diameter. So D1 will be D minus P, so 19 mm, and D2 will be the mean diameter. So the mean diameter is nothing but the diameter of the thread diameter D plus D1, that is this one, divided by 2. So the mean diameter, so D is the outer diameter, and D1 is the diameter at the core of the thread. So you take the average of that gives you the mean diameter. So D is the outer diameter, D1 is the diameter at the core or the root of the threads. Average of that will give you the mean diameter. So we are using this mean diameter in the design, as you have seen the previous equations. And we have the what is called as the coefficient of friction is given as 0.12. So tan phi is equal to coefficient of friction. So from that we will get this angle phi as 6.84. And the lead, it is pitched in number of starts. So it's a double start screw thread, so it is 2 here. So lead is equal to pitch into 2, that is 10 mm. So the lead here is 10 mm. And this phi, it is given as the pressure angle. So pressure angle depends upon the coefficient of friction. So tan phi pressure angle is equal to coefficient of friction. And now we have this, the helix angle of the thread, tan alpha. So in our analysis we had seen that it is L by pi d2, that is the mean diameter. So using this relationship in the analysis, we have this equation, so we can find out the helix angle here. Since lead is known and mean diameter is known, we can calculate the angle, the helix angle, as 8.42 degrees. So once you know this alpha and once you know this phi angle with coefficient of friction, so now we can directly use the equations. We'll go to the torque. So torque applied to the handle. So this torque, what to apply, or the force what is applied here, that is used to rotate the screw thread. So the force is given and you can calculate the torque here. So the torque is nothing but the effort or the force what you are applying at the lever or the handlebar into length of this handlebar. So it is 250 Newton. You are applying the force and into the distance. So the length of the handlebar is 200 mm. So that gives you the torque. So he is taking at in Newton millimeter. So this is the torque which is to be applied at the using the handlebar. So now, but also we know that from our analysis, from the derivation, we had found out that to raise the load, the equation for torque was W d2 by 2 F, that is mu, or coefficient of friction F, and this is the angle, helix angle. So this equation we had derived in the analysis, so that equation we will use now. Anyway, so these equations are there in the data handbooks. You can directly take these equations. So the torque which is applied manually, that is calculated here, and the torque in the analysis to raise the load, what we derived, that equation you are using here. So using both the using this equation, so in this again W is unknown. So d2 is known, alpha is known, coefficient of friction mu is known. So what we'll get is that we'll get the torque with W, unknown value, weight. So we'll get, after substituting the values, we'll get the torque in terms of the weight to be lifted, which is unknown. So when you do that, so we have two equations here. So one equation is the torque, what is required here, and by the analysis the torque was so much. So using equating these two equations, equating this equation and the previous equation, torque, so we'll get the weight which is unknown. So you can calculate the W here. So we'll get 17 kilonewton. So this is the weight we can lift, or the screw jack or the power screw can lift so much of weight, 17 kilonewtons. And for again or designing, you know that for functioning we have the overhauling or the self-locking condition. So we know that alpha here is greater than phi. So in this case, when alpha is greater than phi, we have seen that screw overhauls. That means when you apply this much of load, the load will descend on its own. So that means we are not designed. Actually, this is the screw jack. So we have to design the screw jack for self-locking condition. But here it shows that it is overhauling here. So the design is not satisfactory here. You can say that because alpha helix angle is greater than the pressure angle here, because the pressure angle is based on friction. So the friction is not enough to hold that load here. So it is it is less than the helix angle. So what happens, there will be overhauling, the weight will come down by itself and the screw starts rotating. So but in this application we want that we want the self-locking condition, so we can say that design is not satisfactory in this condition. So what we can do is, this is only to check, we are just checking here. So when the design is not satisfactory, so we can change these parameters, we can change the load, or we can change the other parameters, friction or whatever it is, and we can see that we achieve the self-locking condition. So coming to one more application, we have the shaft straightener, which is shown in figure here. So this is the shaft straightener, and it is required to apply a load of 35 kilonewton to straighten the shaft. So the load applied is 35 kilonewton, and we will determine the force required at the rim of the anvil. So here we have this anvil. So in the previous case we are applying the torque using the handlebar. So in this case we are applying the torque using the anvil, circular anvil, and the diameter is given as 300 millimeter, and the coefficient of friction of the threads is 0.12. So this is actually the screw rod here. So you can see this is a screw rod. At the top we have a anvil of 300 mm diameter, and when you rotate this is a frame, and inside we have the nut here. This is a frame which holds this shaft straightener. So the coefficient of friction is given here, and the buckling is telling you can neglect that. So now you don't have to design for buckling. So at this condition, what is the maximum compressive or shear stress induced in the power screw, we have to find out, and the shear and bearing stresses in the threads we have to find out. So all the stresses, that is shear stress, bearing stress, compressive stress, we have to find out here, and efficiency of the device, we have to find out the efficiency of this screw here. So this is the shaft straightener, and this is the screw which is used inside this frame, and the frame is fixed. So here you can see the load is 35 kilonewton which is applied here, and the thread is given as square 75. So diameter of the screw rod is 75, pitch is given as 6 millimeters, and the height of the nut is 200 millimeters. So this is the nut inside, which is having internal threads, which is connected to the frame here, and this is the power screw or screw rod. So the given data, again we'll first to write down the given data. So weight applied is 35 kilonewton, and the diameter of the thread is 75 mm, and diameter of the anvil is 300 mm, pitch is 6 millimeters, and coefficient of friction you can take it as 0.12. So mu or F. So again we'll calculate the diameters, that is a mean diameter d2 with respect to the outer diameter and the core diameter. So this is the core, this is the outer diameter, and this is the core diameter. So the mean diameter d2 is nothing but outer diameter plus the core diameter by 2. So the core diameter you can get it from d minus p. So the pitch is there, so if you minus that d minus p, you will get the d1 value. So we get this mean diameter, and again we'll find out again this angle, alpha helix angle. So since the lead is given as 6, so it's a single start shaft here, single start screw, lead by pi dm, that is mean diameter, you will get the alpha. So tan alpha is 0.026, so alpha is 1.5 degrees. So first we take the mean diameter, then the lead and the mean diameter, we can find out the helix angle alpha. So again, since coefficient of friction is given F or mu, you can find out the pressure angle here. So that is 6.843. So you can see that alpha, that is the friction angle or the helix angle, is less than the friction angle or the pressure angle. So next we will find out the effort or the load at the anvil, or at the anvil we are applying the load or what is called as torque. So effort into radius of the anvil. So torque required to produce an axial load of 30 kilonewton. So the axial load to be lifted is 35 kilonewton. So using, again coming to the formula which we had derived in the previous cases. So in the analysis of the screw thread, we use this equation, and W weight is given here, mean diameter is taken, coefficient of friction is there, then alpha is there. So all the values are known. You calculate the torque required to produce the axial load of 35 kilonewton. So for this load, what is the torque required to raise the load? That is calculated here. So once you know this, so this is a torque. The torque is nothing but again the load applied into the radius of that anvil. So it is 300 mm diameter, so radius will be 150. So torque is known from this equation, and using that torque is known. So P, the how much load you have to apply on the anvil, is given by torque is equal to load into distance or the radius of that anvil. So you can find out the load which is required, or the force what you have to apply, external force what you have to apply on the anvil to maintain this load of 35 kilonewton. So you have to apply a load of 1, 2, 3, 4 newtons here to get this torque. So once the torque is calculated or the load is known, so the load applied on the screw rod is known, we can easily calculate the stresses in the screw rod. So since it is a compressive stress, so stress is nothing but force by area. The force is the load applied, that is load applied on the screw rod, that is given 35 kilonewton, and d1 is the area, the cross-sectional diameter of the screw thread. So we are taking as d1 here. So it is 69 millimeters. So come back here. So this is d1. So d1 is the diameter at the thread, at the root of the thread, that is 69 millimeters. So that d is taken here, d1 is taken here, and the area of that circular cross section with diameter d1 is pi by 4 d square. So you can easily calculate the stress or compressive stress in the screw rod. It is 9.36 megapascal. So once the compressive stress is known, you can calculate the torsion shear stress. So using the torsion equation, T by J is equal to tau by R. So you can, or directly you can take this equation for the shear stress. So torque is known, just now you found out the torque, and d1, again you take the d1 here. So substitute that and you'll get the shear stress as 2.87 megapascal. And we can calculate the maximum stresses, the principal stresses, sigma 1. So sigma 1, so here the axial load is only sigma here in the one direction. So you take this as sigma x or sigma y. So as is sigma 1, the principal stress or the maximum stress is sigma by 2 plus root of sigma by 2 square plus tau, that is shear stress square. So sigma here is nothing but this stress, that stress, just now we calculated that, and tau is nothing but the shear stress. We substitute that and you will get the maximum or the principal stresses for this screw rod. Similarly, you can calculate the maximum shear stress. So this part is the maximum shear stress. So you can substitute the values equation. All the values are known. This is the direct stress, compressive stress, and this is the torsional shear stress. Substitute that and you will get the shear stress as 5.48 megapascal. So this is how we can find out the different stresses induced in the screw rod because of this load applied or the weight to be lifted. So we have one more problem here, and the screw is triple start screw. With the diameter 50 mm, pitch is 8 mm, and the load is given as 7.5 kilonewton. Coefficient of friction is given, and collar friction we have to ignore that. Length of the nut is given as 48. So we can determine the maximum stress developed in the screw body or the screw rod. Bearing pressure you have to calculate, and you have to check whether the screw is self-locking or overhauling. So again, the data, we take down the data given here. So the weight is given, diameter is given here for the screw rod, which is nominal diameter, pitch is 8, and it is a triple start. So lead is 3 times the 8 here. And the height of the nut, so we have the nut here and they fixed to the frame, so it is 48 mm. Height of the nut is given 48 mm. So we can calculate the bearing pressure here. So again, this D1 is nothing but D minus P. So nominal diameter is given as 50 minus pitch will give the D1, or what is called as the diameter at the root, and this is the diameter, outer diameter of the screw rod. So D plus the inner diameter, the root, divided by 2 will give the mean diameter, average diameter. So next directly we can go to alpha. So tan alpha is, this is a procedure you have to follow step by step to get the different values or different geometrical dimensions of the screw thread. So tan alpha is lead by pi d2. So lead is nothing but pitch 8 here, and it is a triple start, so it is 3, and mean diameter just now we found out. So tan alpha is so much, so alpha will be 9.4 degree. And again, coefficient of friction is given. We can calculate the pressure angle. So the pressure angle is 6.843. So you can compare the helix angle and the pressure angle here. So helix angle is more than the pressure angle. So coming to the stresses again, it is a compressive stress. So force by area, load by area. So area is circular cross section, diameter is d1. So take this formula, calculate the compressive stress. It is same, procedure is same, the formula is also same. So directly you can calculate torsional shear stress, and you can calculate the torque. It is again given in the data handbook, or we have derived this equation for this load W and other values given. What is the torque is, this is the torque here. The 50,246 Newton millimeter is the torque to carry this load, 7.5 kilonewton. So the alpha just now we found out, and the phi is given, and the torque is known, and d1 is known. We can calculate the shear stress. So shear stress is, this formula is there, so substitute that, will get the shear stress 3.45 megapascal. So maximum compressive stress, again the principal stress sigma 1 you can calculate. You can calculate the maximum shear stress, all the values are known. And coming to bearing pressure, so this is height of the nut, so that is pitch into number of threads. So number of threads is 6 here, so we have 8, the pitch into number of threads 6. So actually it is pitch is known, so height of the nut is known, so you can calculate the number of threads in the nut. So nut and the screw rod, they both are in contact, so that will give the bearing pressure or the bearing surface with respect to the relative, or what is called as relative motion between the screw rod and the nut. So you can calculate the number of threads bearing which are in contact when the nut is rotating around the screw rod. So the height of the nut is nothing but pitch into number of threads. So pitch is known, height is known, so you can calculate number of threads as 6. So that number of threads is used here in this equation. So d1, the diameter is given, and d is given. So this is the internal diameter, and this is the outer diameter, and this is the internal diameter of the screw rod, and the load is given. So you can go to this equation, bearing pressure equation, which is given in the data handbook for a particular number of threads. So number of threads is known. So bearing pressure is nothing but force by area. So since the square thread is having 2 diameters, so area will be pi by 4 d2 square minus d1 square, outer diameter minus inner diameter. So and you have to multiply it by number of threads here. So that gives the bearing pressure. So if the bearing pressure is given and weight is given, diameters are given, you can calculate the number of threads also. Number of threads which bear or which are in contact with the screw thread. So again, last is alpha, that is the helix angle is greater than phi. So helix angle is greater than phi means it is overhauling condition. So that particular device, it overhauls. So when you release the force, the load will come down, it will descend by itself. It's a overhauling condition because alpha is greater than phi. You can see here alpha is greater than phi, pressure angle. So when the pressure angle related to friction is less compared to the helix angle, so it overhauls. So friction is less here. So what happens is the load descends when this angle is less than the helix angle. So that's it for this session. Thank you.